process, particularly because we've got some missing content with the electron configurations. And ultimately, that's where these things are coming from. What you're responsible for is knowing the trends for your ionization energy. In general, your ionization increases as we go from bottom to the top in a group. Ignore the blue stuff for the moment. It also increases as we go left to right across a period. Right? That's what this figure is showing. If we take a look, lithium, sodium, potassium, rubidium, cesium are all in the same column, and what happens to their ionization energies? They all get progressively lower, right? When we look left to right across the period, that's where the table becomes a little bit harder to interpret. So let's start with lithium. Okay, if I count lithium, the next element would be beryllium. We're moving left to right. There's beryllium. The next one would be boron. That's the next data point. Next one would be carbon. Okay, so why do they not include all those labels on each of these? Carbon followed by nitrogen, oxygen, fluorine, neon. Why do they not show all of those symbols?
Because they have lithium and neon. So
They put the lithium and neon, so it's kind of implied content. They don't want to put the extra labels on because it gets too crowded. Okay? It's a visual design aspect. It's too crowded to jam those images in there, so they just kind of assume that you can track with that. Okay? Which can be kind of a big assumption. So in general, what happens is we move left to right. Lithium, it goes up, then up, and up, right? So in general, our trend increases as we go left to right on the table. Okay? In our statement of what the rules are, we say in general, and that's because it's not always true. Right? And that's because the rule that we're using to describe that doesn't accurately depict what's actually happening. Okay? So let's take a closer look at some of these. Let's take a look at lithium. And if I was to draw out the electron configuration for lithium, what I'm asking for is where is every single electron located on an atom of lithium. Okay, so when I look at lithium off the periodic table, how many electrons does it have? 3. So what I need to do is say where is every single one of those 3 electrons. This is looking at our electron configurations. The first electron goes in the lowest energy. Okay. The second electron also goes into the lowest energy, 1s. That orbital is now full, so I would then move to the 2s. Okay. That is a pretty extended configuration. I can condense the 1s's to become 1s2. Okay. And we have 2s1. Look at the superscripts. It's 2 and 1. What's 2 plus 1? 3. How many electrons for lithium? 3. Our electron configuration, if you add up those superscripts, will tell you the number of electrons for that atom. Okay. Now let's move to the next element, beryllium. What is its configuration? Well, how many electrons does it have? 4. So its first electron is going to be 1s. The second electron is going to be also in the 1s, so I'll abbreviate, jump straight to the 1s2. The third electron is going to go into the 2s. The fourth electron is also going to go into the 2s because the 2s orbital can hold 2 electrons. And that becomes my electron configuration. Okay? What happened to that last electron? So this is now going to become an important thing to address. So we're actually going to split that 2s2 into 2s1 and 2s1. Ionization energy is the energy required to remove an electron. Okay? And in particular, the highest energy electron. So I'm going to remove the 2s electron from lithium, and I'm going to remove a 2s electron from beryllium. Okay? The 2s electron is located where with respect to the nucleus? So if we just attempted to draw something out here, look at a picture of lithium. Here's my nucleus. Where do I want to draw the 2s electron?
Pretty close.
Pretty close. Okay, so there's my 2s electron. So now we're going to do the same thing, but with beryllium. Okay, beryllium is also a 2s electron, so where should it be with respect to the 2s energy for lithium?
Same place.
It should be the exact same energy. It's the same orbital. There's no difference about it. So I would expect the electron to go to the exact same location. Okay, that same distance away. So this distance is the same. Okay. This goes back to our atomic radii. Okay. Left to right, what happens to our atomic radius? It gets smaller. We said that was kind of a weird concept because we're adding more electrons. Why would it get smaller? Well, should it actually get larger? Where's that last electron going? In lithium, what orbital does it go into? The second energy level orbital. For beryllium, where does it go? The second energy level orbital. Okay. Did I change the distance from the nucleus? No. So left to right, we might say, what happens to the radius? It should stay the same. It does get smaller. So now the question is, well, what else changed? Why would beryllium now get smaller than lithium? What else changes?
The amount of protons.
The amount of protons. So while the electrons are going in at the exact same energy level, I've also increased the amount of protons when I move from lithium to beryllium. Okay, so if I take two magnets and just pull them apart so they just barely don't attract to each other, right? We can all do that? Envision that? Now let's make one of those magnets stronger. What happens? They pull together. Why? Because I made one of the magnets stronger. If I add more protons to this nucleus, what happens? It's going to pull the electrons a little bit tighter. Because the electrons are coming in at the exact same energy level, okay, there isn't an energy level difference to cause the size to change. It's ultimately the strength of the nucleus that's adjusting this. And so we see those electrons get drawn ever so slightly whoa, can't erase that way. A little bit closer. So the 2s for beryllium is a little bit closer. What does that mean for us when we think about ionization energy? What is the point of ionization energy? What are we doing? Taking away that electron. I'm ripping that electron off and placing it in the vacuum. Is the vacuum higher in energy or lower in energy? Higher in energy. Which of our 2s orbitals, lithium or beryllium, is closer to the vacuum? Lithium. It's higher in energy, which means the gap between lithium and the vacuum is smaller, which means the energy, the ionization energy for lithium is now smaller than it is for beryllium. So our ionization energies roughly track with atomic radius. Again, the roughly, we'll look at the exception here in a second.
So for atomic radius, how come francium would be bigger than iodine if it has more protons?
So, and this again comes back to being careful with how we make these comparisons. When we look down a column, hydrogen to francium, what happens to size? Gets bigger. Why? Where is the last electron for hydrogen?
In the first
In 1s. Where's the last electron for francium?
in the billionth orbital.
It's in the 7s. How do I know it's the 7th?
It's the seventh period.
It's the 7th period. The periods actually tell us our energy levels. Okay, how do I know it's S? Because it's in the same column as hydrogen. And if hydrogen's defined as S, guess what francium is?
S.
Also S. Why is francium larger than hydrogen? The last electron is going into a higher energy level. When we look left to right, what's happening? Lithium to boron, or even lithium to beryllium. Is the electron going into a higher energy level? No. So it's going into the exact same place. So when we think about our trends, it isn't that there's more electrons, right? It's where the electrons are located. Down a column, they're located at a higher energy. Left to right, they're not located at a higher energy. So it would be the same distance, same radius. So why does the radius change then? What else changes? What else changes as we move from lithium to beryllium?
The attraction of the electron.
The raw attraction between electrons and protons does not change. What changes when we move from lithium to beryllium? There's more protons for beryllium. Beryllium has 4, lithium has 3. Because the electrons go in at the same distance, stronger nucleus, it gets shrunk a little bit. So when we think about our radii, the explanation for our trends isn't that we have more electrons. It isn't that we have more protons. It's where the electron's located. Down a column, they go to a higher energy level, so it's bigger. Across a row, what's happening? They're going to the same energy level, and the nucleus gets stronger. Okay? Both of those conditions have to be true. Why moving down a column is the nucleus getting stronger irrelevant? It's a different energy level. The energy level trumps. Okay? Does that make sense?
Yeah.
Okay, when we get back to this, lithium now has a higher ionization energy because the electron is held further from the nucleus, which means it's closer to the vacuum, smaller ionization. Beryllium, smaller radius, we'd say, okay, further to the vacuum, that's a larger energy gap. There's our trend. Okay? If it was that simple, then all we'd have to do is compare radii. Boron is smaller than beryllium, okay, according to radius. What happens to the ionization energy for boron? So lithium to beryllium, what happened? The ionization energy goes up. That makes sense. It matches with radius. Boron is smaller radius than beryllium. What would we expect to happen to the ionization energy? It should go up. What did it do? It went down. So there's something else missing in our argument that we haven't evaluated. That something else is our electron configurations. Okay? So now that we've got a baseline trend with lithium and beryllium, what we're going to do is clean this up a little bit. And by cleaning it up, probably make it messier. I'm going to redraw beryllium. Beryllium was 1s2, 2s1, and then we had this last one as our removal. So when I do the ionization, what happens? What would its electron configuration become? Ionization means remove an electron. What electron do I remove? I remove the 2s1, so what's left? 1s2, 2s1. Yeah? Okay. What charge would the beryllium be?
Positive.
Why is it positive? It just lost something.
So you're taking away a negative charge.
I'm losing an electron, and electrons are negative. The net result is that the beryllium becomes positive. Okay? Are we okay with that? What happens to boron? So we'll do the same thing for boron, its electron configuration. 1s2, 2s2, 2p1. I'm going to run the exact same process. I'm going to ionize it. In the process of ionization, what am I going to do? I'm going to lose my highest energy electron, which is the 2p1, and my electron configuration becomes 1s2, 2s2. Well, now it's obvious, right? Why boron has such a low ionization energy and beryllium is much higher. There's actually a couple people saying yes, and I'm really surprised. Is that actually obvious to you?
Makes sense.
Should we try it this way? How many people find that obvious? Okay, so there we go. So what you're actually saying is,
Makes sense. Isn't it because like the 2p1 is further away from the nucleus, so
If
it'd
it's
be easier for it to
further from the nucleus, what would happen to its radius? Boron should be larger than beryllium. Is that true?
no.
No, boron's smaller. So it's not further from the nucleus. So back to the obvious question. Is it obvious? No, accept it. That's fine. It's not obvious. You can tell me that. That's fair. It's not obvious. Should we try that? Thank you. Cool. It's not obvious. Right? So let's repackage this again. Okay. Objective beauty problems. Okay. This was lithium. Sorry, not lithium. Beryllium. Beryllium looks like this, right? Boron looks like this. Okay. Where that is the 2s orbital as my horizontal line. Beryllium, there's one electron in the 2s orbital. Boron, there's 2 electrons in the 2s orbital. Everybody okay with that picture? Okay, which is prettier, red or orange? And don't tell me you like red better than orange. I mean the drawings. Which of those do you are like, that one definitely looks better?
Orange.
Nobody likes red.
That would be
Okay, well, why does orange look better to you?
Symmetrical.
It's symmetric. Okay? And this is kind of a bizarre statement because we're now saying symmetry has some value behind this. Yes. Okay? Because we had some problem with imagination and activity. We'll keep this one simple. We don't have to get up or dance or anything. But I am going to ask that you close your eyes so that I can dance. I'm not dancing. Close your eyes. It's simple. Okay? Think of the most attractive person you know. See, this is why your eyes are closed, because if you're staring at me, this is weird. Okay? Most attractive person you know. If you mirrored the left side of their face to the right side, is that something that you would actually be able to tell that you did? Okay? So if you think about that, I'm just taking the right side of the face, and now I just reflect it across and just drop it on the left-hand side. Okay. Could you actually tell that it was mirrored? Okay. Under most circumstances, you can open your eyes now. No, you can't. What we have determined as humans to be beautiful is symmetric faces. Okay. Who's the ugliest Disney character that you can think of? Kind of an odd statement. Popeye's not pretty. Popeye could work as one that would be ugly or asymmetrical. He's got the little pipe hanging out of his mouth, right? He doesn't have 2 pipes hanging out both directions. He only got one. He's asymmetric. Doesn't he have a little squint to him? Okay. Quasimodo. Like he's supposed to be ugly. That's the whole premise of the story is that he's ugly. Why is he ugly? Because he's a hunchback. He has a hunch just on one side of his body. If he had it on 2, he was going to be gorgeous. Right? Symmetry is something that we as humans find value behind. Chemistry does the same thing. It is a very subtle, subtle effect. Okay? They've done studies on this too. Feel free to be like, beauty, symmetry. You'll find people that have gone through and taken famous people and reflected their faces across. The people that you would classically determine to be beauty or beautiful or attractive have that perfect symmetry. Okay, it's pretty shocking. Chemistry is doing the exact same thing. You all said boron was more beautiful. Okay, so let's apply this. If we go back here, which is more beautiful? Okay, boron or beryllium in that state, once we've ionized, we said boron was beautiful. So we'll call it a beauty. Beryllium comparatively was ugly. That's too mean, so we'll call it a beast. Okay. 1s2, 2s2. What was beryllium's starting state? 1s2, 2s2. So what did beryllium start as?
a beauty.
A beauty. If we look at boron, there are 3 p orbitals. Only one of them has an electron in it. Okay, so if we draw out a representation of that, 1, 2, 3, what do you think? Beautiful or not? In black. Boron, that's not very symmetric. That's pretty beastly. Okay, how does this work for us? Okay, I have a magic stick. Okay, let's say you're beryllium, so you are all beautiful. Yeah. With my magic stick, I'm going to beat you with it, and I will turn you into a beast.
We're not advocating
Okay,
valence.
we're not. It's ionization. We have to add energy. Sorry, there has to be some kind of repercussion to this. How many of you are going to be like, yeah, go ahead, swing away? You're probably going to be like, no, I'm beautiful. Don't hit me with that. Okay, so you're going to put up a fight. By putting up a fight, what happens to the amount of energy I have to put in to get you to turn into a beast? I have to go more. So what happens to the energy of beryllium? It goes up. What happened to boron? So now we flip and you're now boron. You're now a beast. And not like a nice beast like, remember, ugly. Okay? Same deal. I have my magic stick. If I hit you with this magic stick, you become a beauty. You're probably going to be like, you're hitting me with a stick. I don't really like that. But at the end of this, I become beautiful. Okay. I won't fight quite as much. What happens to the ionization energy? It goes down. Both of those happening simultaneously cause the apparent exception to our rule. Okay? In one case, we're making something that was symmetric and beautiful. A beast doesn't like that. Its ionization spikes. In the other case, we're starting with something that's beastly and it's like, I can become beautiful by doing so. Its ionization drops. Because of that, what we end up seeing is the exception, that it doesn't fit the trend. Every single one of these inner peaks that appears to be an exception is the same system. The exact same thing is happening. By looking at the electron configurations and deciding, is that beautiful or beautiful? Is that beautiful or a beast? You can evaluate what should happen to the ionization energy in each of those transitions. You don't need to quantify it, you just need to acknowledge that that would match the trend or that goes against the trend. Does that make sense? Okay. This is why electron configurations become important, because now we don't have to memorize a rule. We can evaluate what we know and just make comparisons of those structures. Okay? Kind of make sense? It's probably my second favorite lecture. It's always fun to talk about beating people with sticks. Okay. That's not true. I don't like doing that. But the beauty beast argument is pretty awesome. Okay? Okay. If we went through and looked at oxygen and nitrogen, we see a very similar system happening. I'm going to leave that to you to take a look at. Okay? So if you look at the electron configuration for oxygen, hit it with some ionization energy, hit it with that stick, remove an electron, what happens to its configuration? For nitrogen, do the same thing. Okay, you guys actually want to work this on your own? See if you can come up with a pattern? Or you just want to move to more content? We can do teams. Like competition teams? No? We can do left and right. Is that a big enough? Are you guys going to actually be able to talk to each other left, right that way? Or should we do like teams of 3? 3s? There we go. We'll do roughly teams of... Nitrogen, we're going from a beauty to a beast, so its ionization energy should be higher, right? Because it doesn't want to make that transition. And then for oxygen, the right side of the classroom is saying it was just beastly to begin with all the way around. There's no transition, which means it should just follow the trend, which would mean that ionization energy between those two should be really similar. And if we look at the trend, it is a significant downward spike. So I'm going to make the argument that the right side of the classroom was wrong on that. They are not both beastly.
Because
Now it is correct.
How is it?
So now let's take a look. Okay, for nitrogen we had what? 2p3, right? Was its starting state, and it went to,
2p2.
and I keep doing that. It went to 2p2. Anybody see beauty or beast in either of those?
2p3, because it has 3.
Shh.
I'm gonna say 2p3.
So, an initial question was, how could P possibly have 3 electrons in it? A single P orbital cannot have 3 electrons in it. The P orbital has 3 orientations. So if we actually split this down, there's 1, 2, 3. When I place the 3 electrons in, we go 1. Where's the next one go? The next one. The next one. I do not pair. Okay? We always leave unpaired unless we move up in energy. Since we're staying at the same energy, I'm going to leave them unpaired. When I go through to look at the bottom circumstance, I still have those 3 orbitals, but now I've removed one. Do you see the beauty and the beast now a little bit? 2p3 is perfectly symmetrical. Okay? It's perfectly half symmetrical, but it's perfectly symmetrical. What happens when we shift over and look at the oxygen? Okay, so the oxygen was 2p4, so it'd be 1, 2, 3, 1, 2, 3. Where's the fourth one go? Now I have to pair. It doesn't matter where I pair, but I have to pair. Is that one symmetrical?
Nope.
No, that is now beastly. What happens when I ionize it?
You take the fourth one away to make the new fourth.
And now it's perfectly symmetrical, and it's a beauty again. Okay? That, to me, is insane. Okay? By looking at the electron configurations, we can predict the relative position of these by looking at Disney. Okay? That is a challenging concept to deal with because you have to be really solidly familiar with our orbitals, how many there are, orientations, fill rates, all of that. Okay, so it becomes challenging. Okay, questions about what's up there? Okay. Because I still don't know why I left that. If we continue through our table, you'll notice potassium to krypton there's all sorts of weird nastiness in it. What's that weird nastiness? So hydrogen is in the first row, followed by our second energy, followed by our third energy. Okay? And so if we look at our rows, first, second, third, fourth row starts with potassium, then calcium, and then scandium. And scandium happens to be D block. The D block elements turn this system into just a giant nightmare. Okay? You get all sorts of different trends happening with those. When you think about the colors that you see, a lot of color comes from transition elements. Okay? When you think about blood, what color do you think about for blood?
Red.
Why red? It's the iron in it. Okay? It's the iron and ultimately the d orbital configurations of iron that cause us to see red. Right? So a lot of the standard colors that we're used to either come from our transition elements or from organic molecules, which is a different beast, so let's not evaluate that.
So are crayons packed with those elements?
They are typically packed with the organic molecules because the organic molecules tend to be less toxic. But it's the same concept. It's just how do we get at those colors or those energies. Okay. So that's our ionization energy trend. Okay. The book does not present the next one, so don't stress a whole lot on this one. It's only in the slides. Ionization energy was removing an electron. What is electron affinity going to be? Adding an electron. So we can go through and do the same thing and say, how do I shove an electron into the atom? Okay? By shoving an electron in, that's now going to require energy, okay? Or emit energy. Instead of, because in the removal, I have to remove that electron, I have to add that energy in. Here I'm forcing it in, I'm going from the vacuum into the atom. That's now a loss of energy. So the sign changes on it, and it can complicate calculations if you were to worry about calculations. In general, the trend runs kind of opposite. Your electron affinity increases left to right, increases top to bottom. This, again, we can kind of use atomic radius to explain this. Hydrogen's very, very small, so I'm taking an electron from the vacuum and trying to put it into the 2s orbital. Where's the 2s orbital? Really, 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 really low, which means there's a large change in energy. Where's francium's 7s orbital? Way close to the vacuum. It requires much less energy to force it in there. Okay? The only reason that I really address this, well, there's two reasons. First reason is looking at charge, because this is going to hit us on the next couple slides. When we looked at ionization, I was removing an electron, so the atom became positive. In electron affinity, I'm shoving an electron into the atom, so the atom becomes negative. So what we're evaluating is pretty much kind of a characteristic of the atom. Does it want to become negative, or does it want to become positive? What are the energies associated with those? Okay. Somebody went through and created a sophisticated formula to compare those and kind of average out those general abilities, and they called that, if the slide moves, electronegativity. Electronegativity is now a pseudo combination of both ionization and electron affinity. Okay? And it is a pseudo combination because in both ionization and electron affinity, the electron is either going to the vacuum or coming out of the vacuum. There's no other element nearby or atom nearby. Electronegativity is now the ability for an atom to take an electron from another atom. Okay? So it's not a perfect comparison to the ionization and the electron affinities. The energy levels change a little bit. But what's useful about electronegativity is I can now predict what kind of charge I would expect on certain elements over others. So for instance, if I take fluorine, and I take a fluorine atom and I put it near a cesium atom, well, they're going to have some kind of interaction between them. That's our bonding, which we'll hopefully talk about here in a little bit. What happens to the electrons when they interact? Well, this is where electronegativity comes in. Fluorine is the most electronegative. This means it has the best ability to attract those bonding electrons. Cesium is the least electronegative, meaning it doesn't want to attract those electrons. So what happens to the electrons in between cesium and fluorine? Where do they go? Should they go towards the cesium or towards the fluorine? Okay, they should go towards the fluorine. We'll address the stay in the middle here in a second. Okay? Which means fluorine has stolen an electron from cesium, which means what happened to the fluorine? It stole an electron, so it gained an electron. This is where we tend to think positive, but it gained a negative thing. Fluorine is now negative. What happened to the cesium? It's now positive because it lost an electron. Deciding exactly where those electrons are located between those two atoms, okay, is it favored to one side or the other or equally shared, is electronegativity. Okay? If the difference in electronegativity is 0, I bond a carbon next to a carbon. Well, which carbon attracts the electrons more?
Both.
Both. So where do the electrons exactly sit? Exactly in the middle. In the case of cesium and fluorine, their electronegativities are so different that it polarizes the electrons, and they only move towards the fluorine. So electronegativity allows me to come up with that interpretation. Oddly enough, it is not mentioned in your textbook. I can't find it anywhere in the textbook, okay, which I find insanely baffling. So instead, if you don't like electronegativity, you can use metallicity as a trend. They're opposites. Where's the most metallic element? Cesium, the lower left-hand corner. Where's the least metallic element? Fluorine, the upper right-hand corner. Okay? Meaning it's directly opposite electronegativity. Okay? So you could use metallicity as a comparison. I think it makes more sense to look at electronegativity. There was a hand.
How come the bottom row and the right row just don't have like any?
So let's look at the right row first. What was the name for the right row? Right row. You just saw it too. What's the name for those? The noble gases. How many of you have interacted with the nobility? In a reasonable fashion. Okay, not with the noble gases, but with nobility, like kings and queens. How many of you interacted with a king or queen?
I've been at the run fair.
That's totally a fake king or queen. That totally does not count. Not prom king or queen. Jeez, come on now. Okay. We probably don't interact with them. Why not? What?
Yeah.
We're all commoners. Okay? So we have to interact with ourselves. The nobility doesn't interact with us. What's going on with the noble gases? They don't interact with anybody. What was electronegativity? Bonding, meaning those two atoms are interacting. Am I going to see an interaction with a noble gas? No. So it doesn't make sense to evaluate their electronegativities because they shouldn't interact with anything. Why is the bottom row not shown?
It's like a lot of them are synthetic.
They're all synthetic. What's the lifetime of most of those? Milliseconds. We haven't observed them in a large enough time frame or concentration to do any studies as to how they would interact with another element. So we can't quantify them. Okay. If we ever did get enough that existed for long enough, we could then start to quantify it. Arguably, it still doesn't make any sense to evaluate them because we're not going to make bonds with them. Okay? So, last, well, not necessarily the last one, ionic charges. Okay, we come up with this concept of isoelectronic. Iso meaning, I think it was same, not equal. Didn't you call that out? Google said the other, but just change it up. Google's wrong, I know.
Wait.
So, same
no, iso
electrons is equal.
I remember what I said the other day.
And same, equal, kind of irrelevant, still gets the same point. Okay? We're saying that when I look at two atoms, if they had the same electrons, I would call them isoelectronic. Could I ever say hydrogen and helium have the same electrons? No, why not? How many electrons does hydrogen have? One. How many electrons does helium have? Two. Okay. Well, what if I looked at hydrogen, but a special hydrogen? This hydrogen we tested the electron affinity on. And in the electron affinity, what happened to it? It gained an electron, which means it becomes hydrogen 1s2. Is that not the electron configuration for helium?
It is.
It is. So I can change the number of electrons on an atom. I can't change the number of protons, because if I change the protons, I change the element. But I can change the number of electrons. The analogy I again like to use for this is you'll notice that we don't have anything specified for the noble gases. Why? Right? They're unreactive. They're the nobility. They're fine the way they are. Virtually everything else wants to do what? Become the nobility. So if I said, I'm going to give you $1 billion, how many of you are going to be like, nope, I don't want it? You'll laugh, so thank you. Okay? Not very likely. You're probably going to accept it. Why do you want to accept it? What do we associate with the nobility? Power and ultimately money that comes with it. Okay? So we can't become the nobility quite like that. But we do want everybody to think that we are better than we are. Okay? And some people don't. And that's cool. I appreciate that. But usually, that's what we try to do. And you're like, no, it's not. Okay? What was the cost of your cell phone? And everybody's going, ooh, that's a hard question. Yeah. Okay. okay? Because you probably spent an excessive amount of money that you shouldn't have spent on that. Why? Because you might have other expenses like food that, say, a rich person wouldn't have to worry about. Okay? But if you have a nice fancy cell phone, what does that then show to everybody else? Oh, look, I've got money. Okay? Throughout history, we do this too. You can look at it with buildings. Okay? There was a period where there were lots of buildings with windows. Like, why do you want windows in a building? Because it was expensive to make glass. So the more windows you put in it, the more you could shout to everybody, I had money. Okay? Atoms are doing the same thing. I want to look like the nobility. So I'm going to change something about my outward appearance. I can't change the protons. I can't change the neutrons to really do anything. So I'm going to only change the electrons. Let's take a look at fluorine. Fluorine wants to look like the nobility. Does it want to look like radon? Those of you are like, what the hell is the symbol for radon? Fair enough. How about xenon? Xenon is a noble gas. Fluorine, yes, absolutely. I want to look like xenon because that's a noble gas. What does fluorine have to do to look like xenon?
Gain electron.
Xenon. Fluorine to xenon. Gain several electrons. We can do better than that. Fair enough. Actually, this morning I couldn't do better than that. It has to gain 45. Yeah?
Sounds right.
Yeah? It would have to gain 45 electrons. Okay? How about krypton? Less. Okay. Better. And this whole numbers thing is plus 27. Which is easier, gaining 27 electrons or 45? 27. So as a target, do you want to try and make $1 billion or $1 million first? What are you going to try for?
$1 million first.
Okay, you're probably going to do the million first, probably because even to make $1 billion, you'd have to pass through $1 million. But okay, so we can ignore xenon. Xenon is now not a target for fluorine. Erase. Thank you. Okay, it works when you shout at it, right? How about argon?
9.
That's a plus. That's a heck of a lot easier than krypton, so I'm going to ignore krypton. That's no longer a reasonable goal. Neon. Ooh. Which is easier, gaining 1 or gaining 9? 1. How about helium? Okay. I could lose, what are we at, 7? 6? Somebody make up your mind.
7.
7 electrons. Which is easier, losing 7 or gaining 1? Gaining 1. Okay. Significantly easier?
Yes.
Yeah. So what happens to fluorine? When it goes out into the environment and it becomes charged, what charge does it become? -1. Why is it -1? Because it's trying to gain 1 electron to look like the noble gas. Right? The easiest noble gas for it to look at. Oxygen, what does oxygen choose to do? Gain 2 electrons to look like neon. It could have just as easily moved to helium, but to move to helium, what would it have to do? Lose 6. Lose 6, gain 2. Okay, gain 2. Nitrogen. Gain 3 or lose 5. Okay, gain 3. Still better, so its charge is 3. Okay, it's not on here. We'll address why it's not on here in a second, but let's draw carbon. What would we expect carbon to do? Could look like neon by gaining 4 or lose 4. Which is easier?
Either way.
Okay.
Well, we're talking about pounds, it's easier to gain.
It's okay. Both are equal, which means what happens? Carbon has both options. So should you memorize carbon? Okay. If I ask you to memorize 1 thing or 20 things, which one are you going to yell at me for? You're probably going to have me, you're yelling at me for making you memorize 20 things. Why? It's too many different states. When we deal with ionic charges, what we're looking at is only the charges that are consistent, that are always true. Carbon is not always true, which means don't memorize it. Okay? You have too many states to possibly memorize. Okay? Let's take a look at aluminum. What's different about aluminum? it became positive instead of negative. To look like argon, what would aluminum have to do? Gain,
4, 5.
you're right, 5. To look like neon? Lose 3, which is easier? Gain 5, lose 3. Lose 3, what happens to it? Becomes positive. But I lost. Why did I become positive if I lost? The electrons are negative. I lost negative charge. Okay? So it becomes a positive 3. In all of these charges, they're all attempting to become the noble gases. That's it. Okay? So you could go through and memorize, except not tin and not lead. You could go through and memorize these, and I would argue that's silly because the periodic table can give you that information as long as you interpret it quickly. The other option, when you get to your exam, you can memorize this for the first 5 minutes. Because when I look at lithium to sodium, what changed? Nothing. The charge? It's the same all the way down. So what I could do as soon as I got the exam and was allowed to start, +1, next one, +2, next one. Arguably, you would write it next to aluminum. Next one, -3, -2, -1. Now you've got those answers. There are 3 that you need to memorize because you don't have a nice trend for it. Those 3 would be zinc, cadmium, and silver. And I'm going to make the argument you only need to memorize 2. You need to memorize silver because it's a +1, and you need to memorize zinc because it's a +2. Why do you not memorize cadmium? It's in the same family as zinc, it's a +2. You now have all of the ones that you're required to have memorized when it comes to the test. Some of these can be derived relatively quickly off the exam. That comes to your decision if you want to do that or not. Kind of make sense? Okay. Sorry, pictures.
Clarification. My favorite.
Homo is same, iso is equal, equi is equal. Oh, interesting.
So remember we discovered last year the Latin roots for things, so you're understanding both language basically matter.
Okay, some quick summary stuff because we do have a little bit of time. Chapter 4, this is everything you're responsible for from Chapter 4. Okay, this will be on the exam, okay, on Thursday. Next Thursday, yeah. I guess everybody knew that better than I did. Okay, good. Next Thursday, not this Thursday. Chapter 5. This is everything you need from Chapter 5. Chapter 4. This is everything you need from Chapter 4.
All the slides are on Canvas.
Yeah, literally all these slides are on Canvas. You already have them. Right. Chapter 5. There's everything from Chapter 5. Okay. Which then sets us up for Lewis structure. The last thing I want to address within Lewis structure, a couple things here. Number 1, Lewis structure is a massive, massive play posit video that is due Friday. Okay, it's a huge hour-long thing. And there's another one coming right after the exam. Okay, there's 2 big ones: nomenclature and Lewis structure.
Can we have to watch them?
Yes. Okay. And you can always pause it. And it does replace the RWS. So it is the equivalent for the RWS. So if you were spending an hour on homework, you now spend an hour on the video. The big thing that I want to address for that is that when we get to Lewis structure, step 1 is the biggest, hardest part of Lewis structure. It is the valence electrons. The valence electrons are literally given to you on the periodic table if you know how to read it. That read it would be the last slide in our slideshow. This is everything that I would recommend you purge onto the exam. It doesn't have the charges written on it, but this is what I would purge onto the exam as soon as you are allowed to start, because it sets up your electronegativity, your ionization energy, your radius, and valence electrons identified by the Roman numerals at the top of the periodic table. Okay? We'll do Lewis structure in lecture on Tuesday.